Welcome back to an intuitive introduction to probability. Currently, we are talking about conditional probabilities. In the last lecture, I tried to give you a first intuitive look at what conditional probabilities are. In this lecture, I now want to be a little more precise and define the give you the exact definition of a conditional probability. So, as we had seen last time, once an event B has occurred, we can think of the state space S shrinking down to B. All the outcomes outside B no longer play a role. They didn't occur. We know B has occurred. So now we want to focus on B and think, what can we now say about this other event A? Before we had probability of A on the entire state space S. What is left of that now on just B? And this gives us now the definition of a conditional probability. The probability of A given B is what is left of A in B. It's the intersection of A and B. In this case, the probability of A intersected B, and we're dividing this intersection probability by the probability of the event B. In some sense, you can think of this, we are normalizing our probabilities on the new state space B, the event that occurred. If that sounds abstract to you, let's look at our standard basic example, a fair die. We have first the event A, an even number, 2, 4, 6, ex ante. Before we receive any more information, A, an even number, has a probability of a half, 50%. The event B are the smaller half of the numbers, the 1, 2, 3, also has a probability of a half. Now, I roll a die and the event B occurs. What now happens to the probability of A? That's now a question for you. Do you think with this information that B happened, 1, 2, 3, does the probability of A happening go up, stay the same, or decrease? Here we do a brief in-class quiz. Please answer this and then it's back to me. Thank you. Okay, thanks for answering the quiz question. Let's now see what happened. So, the die shows a 1, 2, or 3. What does that mean? If it's a 1, A did not occur. If it's a 3, A did not occur. But if it's a 2, 2 is an element of A, then A indeed occurs. So, let's look at the diagram. Instead of the large sample space S, we can forget about this now, we are down to just B. B has now 3 elements, 1, 2, 3. So we see a 2 out of those 3, the probability should be a third. In 2 cases, 1 and 3, A doesn't occur. In the last case 2, A occurs, 1 out of 3. So the probability of A now is decreasing from a half, 50%, to a third, 33.33%. Let's look what the definition of a conditional probability tells us. It tells us to do the probability of A intersect B divided by the probability of B. These are the original probabilities. The intersection probability is 1 in 6, that's just the element of a 2. Probability of B was a half. 1/6 divided by a half is 2/6 or 1/3. And indeed, this definition gives us the correct probability that we intuitively would calculate looking at the picture of just B. To summarize, your original probability ex ante was a half. An even number has a probability of a half. Then you're given the information, the event B occurred. I rolled a die and I tell you B occurred, it's a 1, 2, or 3. Now you update the probability using the conditional probability definition and you realize the probability decreased and so the likelihood is now down to 1/3. Now let me remind you on a concept from a previous module, the concept of independence and dependence. Notice the information of B now changed the probability of A. So the event A, the likelihood of this event, depends on B occurring or not. That now means A and B are dependent. Now let's look at a slight change of the problem. Here now we again have the set A, the even numbers, but instead of B, now we're looking at the set B prime, which are the smallest 4 numbers. So we change B from B to B prime by adding the 4 to that event. Again, I roll a die, you can't see it, and I tell you, listen, B prime occurred. Now we go from the set S down to the event B prime. What happens now? In B prime, we have 4 numbers. 1 and 3 means A does not occur. 2 and 4 means A also occurs. So now the probability of A given B prime, you do the math, is again 1/2. So what happened? Before you said an even number had a probability of 1/2. B prime occurs and the probability hasn't changed. Nothing changed. You're not updating the probability, or if you're updating, nothing changes, it's still 1/2. Does this remind you of the concept of independence from the previous module? Now, B occurring does not make you change the probability of A. In that sense, A and B prime are independent. Let's summarize what we have seen here. I've given you a proper definition of conditional probability. Probability of A given B equals the probability of the intersection of A and B divided by the probability of B. We have seen when A and B are dependent, then the conditional probability is different from the original probability. In the case that A and B are independent, then the probabilities are the same. So the probability of A equals the probability of A given B. We will take another look at these concepts in the next few lectures. Thank you and please come back.